Have you ever thought about being close to the end of the world? The topic of black holes is one of the most intriguing and controversial in the world, so I'll start there. The name cosmic giant comes from the fact that these places are so heavy that nothing, not even light, can escape them. Picture a place where time stops and things look different. Some people are still interested in these things because they make individuals think about what they think they know about physics. In this video, we will explore the concept of black holes. First, let's talk about what a black hole is. A black hole is an area of space-time with extreme gravity that light and electromagnetic waves can't get away from. The event horizon is what sets it apart, and it gives off Hawking radiation. Black holes were first thought about in the 1700s, but they weren't officially named until 1971. They form when big stars break up and can grow by absorbing mass. Astronomers have found a lot of stellar black holes in paired systems, such as the Sagittarius A-star radio source. In 1784, John Michell was the first person to think of the idea of a giant body that could not escape light. He thought that this kind of body would form when the diameter of a star is 500 times bigger than the sun's, and its surface escape velocity is faster than light. But in the early 1800s, scientists discovered that light moves like waves. This led to the development of general relativity, which disproves Michel's idea that a light ray would shoot straight from the surface of a supermassive star, slow down by the star's gravity, stop, and then fall back to the surface of the star. Instead, space-time is bent, which means that the line that light follows never leaves the star, black hole's surface. In 1958, David Finkelstein found that the Schwarzschild surface was an event horizon. This marked the start of the golden age of general relativity. This led to the finding of pulsars, which turned out to be neutron stars that spin very quickly. This finding made people even more interested in compact items that form when gravity pulls things together. The no-hair theorem is one of the more general black hole answers that were found. Black hole physics was made possible by the work of James Bardeen, Jacob Bekenstein, Carter, and Stephen Hawking. In 2016, the first direct discovery of gravitational waves was made public. In 2019, the first direct image of a black hole was made public. The phrase black hole comes from a number of different science terms. The no-hair theorem says that a black hole only has three physical qualities that can be changed on their own: mass, electric charge, and angular momentum. From outside a black hole, these qualities can be seen, but observers outside the hole can't tell you anything about its shape or charge distribution. A black hole's gravity and electric fields don't reveal much about what went in, even when it comes to quantum numbers that are mostly unchanged. The black hole information loss paradox is a peculiar phenomenon. Black holes that are not moving have mass, but no electric charge or angular motion. Even though a black hole's mass can be any positive number, its charge and rotational momentum can only be that number. When a black hole has the smallest mass that still meets this difference, it is called an extremal. Black holes are usually put into groups based on their mass, which is not affected by their rotational momentum. The Schwarzschild radius measures how big a black hole is. A black hole is a spot in space where light and matter can only move toward the black hole's mass. It is impossible for particles to leave because of this change. A black hole is defined by its event horizon, which is a limit in space-time. When a mass is present, space-time changes shape, making it difficult to tell if an event happened in it. This stretching makes an object look slower as it gets closer to the event horizon. This is called gravitational time dilation or gravitational redshift. The event horizon has a circular shape when the black hole is not rotating, and an oblate shape when the black hole is rotating. A lot of the time, singularities in general relativity are seen as proof that the theory isn't working. However, this is a normal occurrence due to the high density and interactions between particles. This should be explained by quantum effects, but no quantum gravity theory can do this yet. The photon sphere is a spherical edge where photons are stuck in a rough but steady path around a black hole. The ergosphere is an area outside the event horizon where things can't stay put, and the innermost stable circular orbit, ISCO, is an area where very small changes cause objects to fall into the black hole. The last area that can be seen around a black hole is the falling region. People have long wondered if black holes really exist or if they are just weird answers to Einstein's theories. Einstein at first thought that black holes couldn't exist, but some relativists kept saying that they were real things. Most experts believed none could prevent an event horizon from forming in the 1960s. The Kerr solution, the no-hair theorem, and the laws of black hole thermodynamics made it clear that black holes' physical properties were simple to understand, which meant that they were beneficial study topics. Black holes usually form when heavy things like stars fall apart under their own weight, but they can also form in other ways. For gravity to work, there must be a lot of matter, which is not enough for a black hole to grow. Even though the early universe was very dense, it did not fall back into a black hole during the Big Bang because it was expanding faster than it was pulling in. It is possible for black holes to form in high-energy collisions with enough mass, but as of 2002, no such events had been found. Based on this, we can say that the smallest black hole mass is probably around the Planck mass. Some new developments in quantum gravity show that the minimum black hole mass might be a lot smaller. This means that micro black holes could be made in the Large Hadron Collider at CERN, or when cosmic rays hit the Earth's atmosphere. Black holes can also get bigger by taking in more matter, joining with other things, and sending out Hawking radiation. Hawking radiation, on the other hand, is thought to be very weak and difficult to spot from Earth. If black holes disappear through Hawking radiation, a black hole with the mass of the Sun will disappear in 10 to the 64 years, while a black hole with 2 times 10 to the 100 times the mass of the Sun will disappear in about 2 times 10 to the 100 years. Some monster black holes may keep growing as superclusters of galaxies fall apart. Indirect views are often used to figure out what black holes are because they don't give off electromagnetic radiation. The Event Horizon Telescope, EHT, is a live program that looks directly at the area around black holes' event horizons, like the one in the middle of the Milky Way. EHT began to look at the black hole in the middle of Messier 87 in 2017. The EHT showed the first straight picture of Sagittarius A star in 2022. This is the supermassive black hole at the center of the Milky Way. The picture showed the same ring-shaped structure and round shade as the M87 star black hole. Back in 2015, the EHT found magnetic fields just outside of Sagittarius A star's event horizon. In April 2023, a picture of the shadow of the black hole in Messier 87 and the high-energy jet that goes with it was shown. Scientists have watched the proper motions of 90 stars close to the heart of the Milky Way and found that they are circling a supermassive black hole. To figure out why those stars move, they have known since 1995 that a 2.6 times 10 to the 6th solar mass object must be inside a volume with a radius of 0.02 light-years. Since then, one of the stars, named S2, has gone around the Sun once. The object that is moving those stars around has been fine-tuned to have a mass of 4.3 times 10 to the 6th solar mass and a radius of less than 0.002 light-years. Some observations suggest that this object may have an event horizon, which is something that only black holes have. Up to 40% of the mass of matter that falls into a black hole as radiation is released is one of the most efficient energy sources. Scientists have found that supermassive black holes, which can be millions of times stronger than star black holes, are found in active galactic nuclei, AGN. There is a central black hole, an accretion ring, and 2 jets in these AGNs. The M-sigma relationship points to a link between how the black hole formed and how the galaxy formed. It is also possible to see gravitational lensing in stars moving around the black hole. The evidence for stellar black holes rests on an upper limit for the mass of neutron stars, which is based on assumptions about how dense matter works. This limit could be raised by new strange states of matter which could lead to dense quark stars or preon stars. Supermassive black holes are not as dense as star black holes, and for black holes to not form, general relativity must fail as a theory of gravity. The Beakenstein-Hawking entropy of a black hole tells us how crazy it is, and it changes based on how big the black hole is. Hawking discovered in 1971 that the total area of the event horizons of classical black holes can never get smaller. This is called the second law of black hole physics, and it is similar to the second law of thermodynamics. As a black hole gets bigger, its entropy goes up instead of down, which leads to the hologram principle. The black hole information conundrum, which asks if information really does get lost in black holes, has caused a lot of disagreement in the field of theoretical physics. When unitarity and the conservation of energy are broken in quantum physics, information is lost. New evidence shows that when the problem is fully treated in terms of quantum gravity, information and unitarity are maintained. It is said that black hole complementarity can solve the information paradox, but the firewall paradox in 2012 shows that it can't. You have reached the end of the video. What are your thoughts? Let me know in the comments. Please don't forget to subscribe for more videos. See you in the next video.